So hello to everyone, and after 1 day and a half of spectacular garnets and high-grade rocks, now it's time for weird stuff, and we talk about low-grade metapelites. And why low-grade metapelites? Because they are very common and widespread in most of collisional chains and orogenic wedges, and they record very well different stages of the deformation. We could see different granulation cleavage and spoliation. But when we talk about PET estimation in low-grade metapelites, we have several problems. First one, we have the presence of few index minerals like chloride, quartz, and white mica, so involving high variance assemblage. And this is a big problem when we talk about phase equilibrium modeling. The second one is the presence of a mosaic of local equilibria. And this is valid also for high and medium grade rocks. And here we have chemically disjunct minerals and phases and detrital phases. So it's difficult to find a well-equilibrated assemblage. And the last one is the presence of a grain size that is very small. So we have several problems to distinguish different phases, and we have to involve high-resolution techniques. So up to now, we have many methods to obtain a PET condition in low-grade metapelites. The first one is very common, is Vitale reflectance that give us temperature. We have different methods that involve the crystallinity of different phases, like now it's very common Raman on graphite, that give us the peak of temperature. We have conventional thermobarometry, now progressing to multi-equilibrium approaches with the PET estimation, and the classical phase equilibrium modeling with the prediction of the mineral assemblage and the mineral composition and the using of the isoplate intersection. So we want to compare different methodologies, and in order to do this, we sampled three samples. We took three samples from the Sardinian belt. The Sardinia island is in Italy, and it represents a part of the Variscan chain in Italy. And it is made by the hinterland in black, made by high-grade rocks. The foreland in the southwest part, made by the composing by the external zone, and the hinterland-foreland transition zone made by the napped zone. And this sector is made by low-grade metamorphic rocks that made the internal and external nappes. So we haven't got any constraints to distinguish internal and external nappes. And we also have a truss that divided two different nappes that are very close together. And we sampled two from the internal and one from the external napped zone. And the samples are very close. And we want to understand if there are any variation in the PET constraint. So these are the three samples. And as is very clear, they show similar microstructure. They are made by accumulation cleavage. We have a red exfoliation inside. We have a main foliation that defines the SP. And we select an homogeneous and a small area where in this area is present all the mineral assemblage made by potassium white mica, quartz, chloride, and albite, except for AP 1949. And we use map tools and in order to calibrate the map. And here we have the modal distribution of different phases. So all the samples are very similar under the microstructural and mineral point of view. But we investigate also the mineral chemistry. And here we have the silica and the X magnesium for the potassium white mica and the chloride respectively. And as is very clear, the white mica is quite homogeneous. We have some parts that are solid. And we use not the microstructural position because it's impossible to define two different groups under the microstructural position, but use the amount of silica in order to define two different groups, one with high silica and one with low silica content. But the X magnesium is very similar in both groups. About the chloride is more homogeneous, and the silica and the X magnesium are very large in the range. And we use a proxy of temperature that is very common for low-grade chlorides, and is a number of vacancies in order to define low temperature or high temperature chloride in function of the number of vacancies. But as is clear in this map, we have a second generation or a late chloride that is not in equilibrium with the maps that we have. And in order to investigate samples that display microstructure that are similar, but also a similar mineral chemistry, we excluded this sample showing a second generation of chloride not in equilibrium with assemblage. So we start with the PET estimation, and we start with the multi-equilibrium approach involving chloride and white mica. And this approach involves the equilibrium between chloride and white mica in presence of quartz and water. And this approach is made by Vitale and co-authors. And here we have the internal napped zone sample, and here the external napped zone. And both, we use the two groups of chloride, the high vacancies chloride and low vacancies chloride. And we have two different stages, one at relatively higher pressure condition and one at lower for both samples. But this method requires a huge assumption, that is the chemical equilibrium between chloride and white mica. So generally we use the proximity or the boundary between each phases, but here it's very difficult to understand if chloride and white mica are in equilibrium. So in order to compare these results, we use an hybrid approach that involves Raman spectroscopy on carbonaceous material with the white mica multi-equilibrium. And Raman spectroscopy is based on the increasing crystallinity with the increasing temperature of the graphite, whereas the potassium white mica multi-equilibrium is based on the amount of water in the interlayer side of white mica. And here we use the two group of white mica, one with high silica and one with low silica content. And also here we have two different stages in both internal and external nappes, one at higher pressure and one at lower pressure. So if we compare, but before it's important to say that this method requires an assumption, that is the potassium white mica must be formed at the peak temperature of the Raman spectroscopy. But if we compare both methodologies, we obtain similar results. We have two different groups indicating the two stages, one at higher pressure and one at lower pressure for both nappes. And in particular, we highlighted a shift in the pressure, so decreasing pressure for the stage 1 to the stage 2. So it's very clear that we have two different metamorphic conditions for both samples, and also we highlighted a difference in pressure and temperature of both nappes. But as I said you before, we want also to try to compare these results with the phase equilibrium modeling of low-grade metapelite. And we use Tediac Domino with 5 different databases, 2 based on the Holland and Powell datasets, and 3 made on the Berman datasets. And the first part that we want to analyze is the prediction of the mineral assemblage. And here I put 2 examples. One is example of the chloritoid, and one is example of the albite. And the chloritoid is very important when we talk about high pressure metapelite, because it's very common. And for the internal napped zone sample, most of the databases predict chloritoid, but we haven't got it inside. And it's very important that for the last database made by Holland and Powell, based on the solution model of Y, we have chloritoid at condition slightly upper for more than 0.6 picopascal. That is the upper limit of the stage 1, which I showed you before. And about external nappes, only June 92 and SPARC predict chloritoid. So it's quite pretty good. But when we talk about the albite, and albite is present in both samples, we have a big problem, because all databases mostly predict lack albite, but we have albite inside. So here we have a problem with the prediction of the albite, and generally is representative for all databases. But another parameter that we want to test is the prediction of the composition, so the classical isoplate approach. And here we put the example of the potassium white mica. And here we have the isoplate for the silica in white mica and the X magnesium in white mica for both internal and external nappes. And as is clear, not all databases were able to predict our natural composition. And here with the thick line, we have the average of the measured values. And with the shaded part, we have the entire range. But this figure maybe is more clear, because here we have the histogram representing all the possible values that this database could predict in the PT space for both samples. And here in orange and in yellow, we have the range that we measured with the microprobe of the internal and external napped zone samples. And about the X magnesium, the modeling is quite pretty good, because all databases are quite in agree with the measured composition and values, except for June 92. But when we talk about the silica and white mica, for example, only 2 databases partially overlay the natural range in values, whereas the other databases are not on the measurement. So the big take-home messages is that multi-equilibrium approaches integrated with different approaches like Raman spectroscopy and Carbonaceous Material give us similar results, and maybe they are in agreement for both samples. And isoplate and Tesago approach on low-grade metapelites may reflect several problems, like I showed you before about the silica and white mica. And people must be careful when using this approach, because most of the tectonic interpretation on low-grade metapelites when you use phase diagram approach are based on the silica and white mica isoplate. And it's important to say that maybe we could use an approach on low-grade metapelites, but may be validated and tested by integration different approaches like Raman spectroscopy on multi-equilibrium in order to compare different PT estimation. So thank you for your attention.
Great talk. Are there any questions?
Yeah.
Yeah, there's certainly some problems with the white mica models. You looked at your micas for something like TEM, because these low-grade rocks, some of these micas could be very complex intergrowths of multiple different micas. You looked at them in really fine detail.
Yeah. In one sample, okay, here I put only the example of chloritoid and albite, but inside our sample, one of the samples show the presence of paragonite, because it's very common that we have paragonite interrelated in white mica, and maybe paragonite could act a big problem in the sodium budget of the rock, and maybe could be linked to the albite prediction or not. And also the reaction between the presence of paragonite instead white mica would act in the silica alumina reaction, and maybe could change something about the silica and white mica. So this is a sodium problem that could reflect in the white mica, in the silica photo.